All right, we have just very briefly gone through our table of indefinite integrals, all of which come from our knowledge of derivatives. So the more derivatives that you have memorized, the more integrals you have memorized. But let's take a look at a couple of examples using these rules. So let's evaluate the integral of 10x to the fourth minus 2 secant squared x dx. All right. Now, we know that when we have the integral of a sum or a difference, we can split it up into the sum or the difference of the integrals of those functions. So we can take the integral of each term. And we also know that those coefficients can go out front. So we can write this as 10 times the integral of x to the fourth dx minus 2 times the integral of secant squared x dx. And then we can integrate each of those separately. So we've got 10 times, well, the integral of x to the fourth is x to the fifth over 5 plus a constant, but we're going to leave the constant for the end because each one of these is going to give us a constant, and the difference of two constants is another constant. So we don't need a constant for each. So we've got, that one was x squared over 5, and then minus 2 times, what is the integral of secant squared? You might remember, but if not, you can look in our table up here, and that is going to be tangent of x, and then plus a constant. And we know that in that first term, 10 divided by 5 is 2. So we end up with 2x to the fifth minus 2 tangent x plus a constant. Now, an interesting question is, how do we know that this is correct? Is there any way to check our work and see whether or not we made a mistake? And the way to check an integral is by taking the derivative, because those are opposite operations. So what we can do if we want to check is we can take the derivative d over dx of what we have, 2x to the fifth minus 2 tangent x plus a constant. And we can differentiate each of those terms separately. The derivative of x to the fifth is 5x to the fourth. And so that's 2 times 5x to the fourth minus 2 times. And the derivative of tangent we know is secant squared. And then the derivative of a constant is 0. And then 2 times 5 is 10. So we've got 10x to the fourth minus 2 secant squared x. And that is exactly what we started off with. So we know that unless we've made two errors that have kind of canceled each other out, we know that we have indeed integrated correctly. All right, let's do one more. Let's evaluate the integral of cosine theta over sine squared theta d theta. Now this is a little bit challenging because we don't have this in our table, but we might be able to play around with things a little bit and get something nicer. What I'm going to do is I am going to take this, I'm going to write this as a product. The denominator, I'm going to split up the signs. And cosine theta is 1 times cosine theta. This is just another way of writing it. But we know that 1 over sine theta is another one of our trig functions, and the same as cosine over sine. So that might help us write things in a different way. What is 1 over sine of theta? Well, that is cosecant theta. And cosine over sine is this inverse of tangent, which is cotangent d theta. And if we look at our table here, we do have the integral of cosecant cotangent. That is negative cosecant. So that's going to be negative cosecant theta plus a constant. So we're not going to end up having a table for every single function in the universe. That would be far too many to memorize. So we're going to have to develop different strategies for solving integrals, and one of those is going to be to figure out if there's a different way of rewriting our integrand in a way that matches something that we have in our table. So those are a couple of examples, but I have several more examples that I really encourage you to go through. The more practice you get with these, the better prepared you'll be for Calc 2.